Welcome to Walkabout the Galaxy, the unpredictable astronomy podcast where the science is universal, the opinions are personal, and the hosts come and go. We are Strange, Charm, and Top the Astroquarks, also known as Josh Caldwell,
Addie Dove.
And Jim Cooney.
coming to you from the internet. Is it the internet or the World Wide Web these days?
I think
Or
it's
does it
definitely
matter?
the internet.
It's
the
definitely the internet.
interwebs.
The World Wide Web probably just dates me. Welcome back, Jim.
Thanks.
We miss Hannah, but you'll do in a pinch. And one of these days we'll all be together, unless there's some sort of astro quark exclusion principle that I'm not aware of. Remember to subscribe to us on all platforms, including YouTube, Facebook, Twitter, and Instagram. Our YouTube videos now feature chapter breaks, so you can cheat and go straight to the trivia answers, and also silly shorts, the kind that you watch on YouTube, not the kind that I wear sometimes. Speaking of things I wear, we are also at www.walkaboutthegalaxy.com, where you can order a Walkabout shirt and support STEM education at the same time. You can contact us anytime at wtg@ucf.edu, and please do contact us that way if you order a shirt, so we can be sure to make you a happy Walkabout shirt wearer in short order. Our stumper today is, of course, telescopical.
Ooh.
You know where this is going, right, Jim?
Yeah.
HST or JWST.
Oh no!
Ooh.
It's a tough one. HST has been very, very good.
I'm letting you go first, Jim.
All right. I'll go for HST. You got to prove yourself to me, Webb. I am, of course, blown away by the first images. We'll get to that in this episode, but HSP has been doing it for a hell of a long time and has really radically changed our view of the universe. So go HST.
Yeah, HST. What about you, Addie?
Well, I mean, I'd like to see Webb's images in the optical, and then we can. Just kidding. It can't. I mean, I love Hubble, right? It's so good, and I feel terrible for Hubble. It's been every time you see these comparisons with JWST, and it's like, here's the old crappy images from Hubble.
Yeah.
It's like, here's your flip phone camera, and here's your iPhone 13 camera.
Yeah.
I think I'm gonna say Hubble also.
Oh, we're showing our age here. I think I would have to say Hubble just because I've got a sort of an ultraviolet bias.
Oh yeah.
And
that's true.
With from my own research. And so gotta love a telescope that can see in the ultraviolet. And we shouldn't forget all the amazing things it's done. But today is mostly going to be about JWST and the amazing really, for the engineering aspects of it, JWST is pretty amazing, and I've just
absolutely remarkable. I still, even though I've seen the images, I cannot believe it worked.
I know, right? Yeah. So many. I've been reading through and going back to like December when it launched, and I'm thinking how sick to their stomachs everybody on that project must have been until that launch went off successfully, because like launches are, not 100% successful. In fact, I'll have a little bit of space news about that. Well, today we will talk about the first observations made with James Webb Space Telescope. But first, this episode of Walkabout the Galaxy is brought to you by Hohmann Transfer Orbits. For the perfect combination of energy efficiency and schedule, take a Hohmann Transfer Orbit for your next walkabout the solar system. This semi-elliptical path between the planets can be tuned for your favorite destination no matter where you start. With a neat, free trajectory halfway around the sun, the Hohmann Transfer Orbit blends simplicity with your need to get where you're going quickly. Use our free orbit calculator to determine the optimum time for your launch and all the delta V you'll need. Then set your sights on Olympus Mons or the moons of Saturn. Let the solar system be your playground with the Hohmann Transfer Orbit. Movement that inspires.
You said semi-elliptical. What does that mean?
Half an ellipse.
Half an ellipse. Okay. I was going to say,
That's
is
what
a
I mean.
semi-ellipse a shape? I guess it's half an ellipse. Yeah.
Semi means
What was
half.
the what was the
And I
phrase?
thought
No,
that might get you because
colloquially.
people,
So yeah, it could be colloquially semi, right?
colloquially, semi means kind of elliptical,
Kinda,
Yeah.
right?
kind of an ellipse.
But the semi-major axis of an ellipse is not kind of the major axis. It's half
No,
of the major axis.
Right.
stupid English language.
Yes.
What was
Movement,
the phrase?
movement that inspires, movement that inspires.
Movement that inspires. Um, Dyson.
Interesting.
Reebok.
Oh, I like that.
Interesting. It's actually Kia.
Oh, of course it is, Josh. I
Right.
should have guessed.
Yes, we're shopping for a
Josh
Kia.
is, yes, Josh is shopping for a car. You know what I don't like? Kia's new logo or name logo.
It
It
just
just
says
looks like
Kia,
it's just
doesn't it?
yeah, but it just looks like KN to my brain because they like
Oh,
merged it so it's one. It's like the worm, the NASA
yeah,
worm, where it's all like a
like the
flowy
NASA
thing.
worm.
Yeah,
Yeah,
I don't like it.
yeah. What's your favorite car logo? There
The
is a right
Pleiades
answer.
Subaru.
one. It's got to be the
Subaru.
Pleiades.
Exactly, Subaru. Subaru. Okay, I'm just making sure. Just making sure. It's Subaru, which has a picture of the Pleiades, because that's what Subaru means. Yes.
I
Okay.
like how Jim
So
said the Pleiades.
the Pleiades
I
one,
couldn't even
right?
remember which car company it was, but the Pleiades
The
one. That's the
Subaru.
one.
I did have a Saturn for many years, Josh, which is also good for astronomy.
So so did I. Yes, and
Yay.
it was a great car.
It was,
Um,
yeah.
so the space news that is a little bit related to the nerve-wracking moments on Christmas Day of 2021 when James Webb launched. Uh, how many launches do you think orbital launches do you think there have been this year so far?
Oh shoot, I just
In
saw this. Is this the
2022,
trivia?
it's just a free bonus trivia. It's free, no
Oh right.
charge. Yes. So we're July 15th, 2022. And just to remind you, like the most orbital launches ever in a year were sort of in the mid 100s, if I recall correctly.
I think we're at like 60 or 70 already. No.
It's actually 84 already.
I was gonna say maybe 80. Yeah. I heard that number recently
84,
and I was like, what?
yeah, a large number, 84 orbital launches, but three of them were failures.
Yeah. Did you
So we're
include the one that just
still,
launched yesterday?
I believe I did, but I didn't do a manual count. But we had a beautiful launch from here last night here in Central Florida. Yeah, so, we're still at sort of like the 5% failure rate, which when you got a $10 billion space telescope riding on your rocket is cause for some nail biting.
Well, but a couple of the failures were like smaller, less demonstrated rockets.
Fair enough. Right. It's definitely true that the more tried and tested big launch vehicles have a better success rate. They're,
Yeah.
including like 100 in a row or something. So I'm being a little bit disingenuous there with that. Um, of those 84, only four, or maybe four, I don't should say only four had people on board.
Yep.
Interestingly,
None of those were ones that failed.
right.
Yes.
Interestingly, only two suborbital missions so far this year with people on board. So there have been more orbital missions with people so far this year than suborbital missions, even though for several years now we've been like, okay,
It's gonna
there are going to be
happen.
these joyrides to space on these suborbital launch vehicles for all these rich people, every week or something, and it's just not happening. And I
Yeah.
don't
Well,
know
part of
why.
that also somehow it's already more than halfway through the year. Which I was just like, oh, but there's still time in the year, but there's not. Um, yeah, well, I mean, Virgin hasn't flown at all in quite some time, right? So
Yeah, I had a payload on their last flight. No,
no,
I didn't. I had a
no.
payload on their last non Richard Branson getting a ride to space flight. Yeah. Well, now I've got a sort of follow up stumper before we start talking about JWST images, which I'm sure is
Oh, we went.
infuriating all of our.
Now we're doing follow-up stumpers. Holy cow!
I know.
I'm infuriating all of our listeners. We'll come back to that.
Just talk about the JWST images.
Let's just talk about JWST. Damn it! So they released 5 data products. I can't really say 5 images because one of the things they released is a spectrum. And
I mean, you can download it as a JPEG.
I do have a picture of the spectrum up here. Why don't we start with that one, since it's maybe the less visually stunning. This is a spectrum of the atmosphere of an exoplanet.
Yeah, I would suggest if you're following along listening, it's going to be a little difficult, but we'll describe them to you and then you can look afterwards or before. But if you can also, and you're not driving, you can look them up on the NASA website.
So this is
this is the one that probably
WST 96b,
but maybe the coolest.
Some people care about it a lot, but it's not as visually oh my god, knock my socks off.
This is, I would say, when I did a radio interview earlier this week about these, and they was asked what I was most excited about, and I had to say honestly, this one, the squiggly line. And what we have is a squiggly line which shows the near infrared absorption spectrum of the atmosphere of the exoplanet WST 96b.
And you know what's more exciting than looking at a squiggly line? Someone describing
about it. I'm not going to describe it. I'm not going to give any more description to the squiggly line than say it's a squiggly line.
It comes down and then it jumps up again.
I don't really care what it looks like, except that it's good quality data.
It's so many data points.
And it shows that there is water vapor in the atmosphere of this planet. And I don't even really care that much about water vapor in the atmosphere of this planet. I just care that we can see it.
Yeah.
Which means we're going to be able to see all sorts of other cool stuff like that.
Yeah. I mean, it's interesting, right, that they released just this spectrum. So it's light between like a certain wavelength that has a lot of water bands, right? And it's a transmission spectrum. So they observed a planet going in front of the star. They observed the whole transit, and out of that they pulled this transmission spectrum, which is light coming from the star through the atmosphere to the telescope. And from that, they can see where there's dips and bumps and stuff like that, how much water there might be. And the plot that they revealed is amount of light blocked and in parts per billion.
Yeah.
Jeez. Yeah. It's really amazing how much better this is than what we had before. We in fact here at the University of Central Florida have a group that works really hard trying to pull data like this, but they're working with like 4 or 5 data points, right? And trying to
2 sometimes, yeah.
And here it's just like data all over that plot, and so that the improvement in our ability to see these gases in these atmospheres, specifically water, I guess, in this range, is remarkable.
Yeah,
and it's I have to. I don't know if you guys know this, but I worked on the Cassini mission for a while.
No way.
And we actually
might not have known that.
We made a measurement that is qualitatively identical to this, or I shouldn't say qualitatively, but whatever, the same exact kind of observation, looking at the atmosphere of Enceladus.
Ooh.
As light from our star, the sun, shone through the geysers of Enceladus, and we measured its spectrum with our ultraviolet camera on Cassini. Same exact technique. First, you have to look at what does the spectrum of the star look like without the thing in front. Then you look at it with the thing in front. Then you subtract, and you get the spectrum of the thing in front, and modeled it. That I'm way down the author list on that paper, but it is my most highly cited paper,
nice.
Which showed that is the paper that said this stuff coming out of Enceladus is water vapor. And now we have that kind of thing, not for a moon in our own solar system, but for a planet around a freaking star over 1,000 light years away. So that's
crazy.
Pretty amazing. Yeah. Okay, let's talk about some of the cool pictures then.
Okay.
Jim, or Addie, what's your favorite?
My favorite is the image of the Carina Nebula.
Why is that?
Well, because A, it's beautiful. But B,
It is.
my daughter's middle name is Carina because of the Carina Nebula and the Carina region, constellation. I
It is
couldn't
a
avoid there.
constellation. It is a
Yes, so the
constellation.
Carina Nebula is in the constellation Carina, which is where it gets that name.
I will say I do agree that that is the most visually stunning of them. It's not my favorite, but it is the most visually stunning.
Also, it's pretty amazing because it's dust. Oh,
Yeah.
so that's another
One
reason
of
it
your
can be.
favorite things.
I love dust in space. And it's starbirth regions, right? So the Carina Nebula image is this like great, beautiful sort of landscape image where it's got the sort of I will say they've colorized all these images spectacularly, right? So these are all
They
the
have.
images we're seeing are infrared images. So it's not light that our eyes actually see. So they've
Right.
used the spectrum that they have, which goes from shorter wavelengths to longer wavelengths, and they've colorized them like we do for optical, which is what our eyes see, right? So like shorter wavelengths are blue light and longer wavelengths are red light, and so that's how they're colorized in these images.
And
Um,
I agree. I think they did a beautiful job with it. And that's one of the things that surprised me the most is how much these pictures, they were able to make them look like pictures that would be taken with Hubble in the
yeah,
optical visual part of this of the spectrum.
yeah,
It's important
Yeah,
that
and
we're
they're
mentioning this. Well, I'm sorry. I was going to say it's important that I'm mentioning this because I've seen a bunch of like these like sliders and things like that where you can compare the Hubble image of the same thing to the Webb image. You got to be really careful with that. They're in very different, not very different, but in definitely significantly different wavelength regimes, and so uh,
yeah,
you're not really you're comparing apples to oranges in some sense when they're comparing Hubble to Webb.
right. In
yeah,
some sense, they should be combined into some amazing trans-spectral composite that goes from the ultraviolet
yes,
through to the infrared.
Yeah,
But Addie, you were mentioning we're seeing dust, and that's like the whole point of Webb looking at these other wavelengths is it sees different things than Hubble and our
yeah,
ground-based telescopes can see. And so it's not just a question of like, oh, it's a bigger mirror, because there's a lot of talk about the mirror is so many times bigger than the Hubble mirror, which is true, but because the wavelength of light that it's observing is also bigger, that dilutes some of the benefits of that larger mirror, because one of the
yeah,
things you get from a telescope is based on the ratio of the mirror size to the wavelength. Um, so it is, as Jim said, it's not a straight up um, even comparison to compare the two, which nevertheless is what we've been spending half this episode doing.
but yeah, so it's beautiful because it's those star forming regions. So there's a lot of dust and gas that's in these complex formations, and these are like where stellar nurseries are formed. So this isn't like a protoplanetary disk, like what we talk about a lot, but it's where part of these regions are where protoplanetary disks and where planetary systems can form. And it's this complex areas of gas and dust, and you get these like blobs that are denser, and that's where you have things. And the other thing about this image, and we'll talk about it in some of the other images, is that like there's stars in a lot of these images, and the stars all have a very specific, they very very six-pointed star diffraction,
Yes,
um, which has to do with which is a very characteristic um, it's a characteristic of all JWST images apparently,
right.
where it has to do with the mirrors and how they're structured.
Yeah. So there's a six-armed support, and then there's like six big diffraction spikes, and then there's two smaller diffraction spikes. And I
Yeah,
think we're all going to become very, very, very familiar with that particular pattern. It'll make JWST images instantly recognizable because of
yeah,
that very specific diffraction pattern that they'll have on the point sources. But it is a spectacular image. And what it shows is this, they call it the cliffs of creation or something like that, because we see this a very sort of sharply delineated edge of the nebula that is uh, in the longer wavelengths that glow from dust in the nebula, and then beyond it, the deep dark blue. Really, I don't know. It looks like space looks in the Guardians of the Galaxy movies. It's like when I go to
yeah.
those Guardians of the Galaxy movies, like space isn't that bright and colorful,
I know.
but it kind of, but picture kind of looks like what
It
space
kind of
looks
is.
like in those movies.
Yeah,
Yeah.
it's great.
So, and I feel like, all these JWST pictures, this first set, sort of capture a kind of like circle of life kind of
Yeah,
thing.
they did a good job of a variety of images and like a variety of topics, and then also like very distinctly um, exciting images, I think.
Yeah. And I encourage people to like go check out these images. You just Google JWST
Just
first images, go to NASA
boggle them.
website, and get the full high res images. They're
Yeah.
free, right? So
We'll
never
put
pay
links
for
on our
these
website.
images, by the way. If somebody's selling them to you,
Yeah.
they're free, okay?
Well, unless
Uh,
it's like a nice printing, then you might pay for it.
if they put it on a T-shirt, the T-shirt is worth something, right? But
Yeah.
the digital images you paid for with your tax dollars, and
Yes.
they're really really high resolution. You can just zoom in and sort of wander around these fantastic nebula, these
Do a
eclipse of
walkabout
creation
in
in
your own images.
your own. Yeah, and imagine all the sort of cool things going on there with star formation and such.
Yeah.
So
Jim, what's your favorite?
Well, you could probably guess. I don't. Well, they're all great, but the SMAX 073, uh,
Max.
which was the first. I don't know why they like put this one out a day before the other handful.
I don't either. And I don't know why they
PR
chose that
stuff,
one. Yeah, but like
the
that's
deep
the one
field.
that having people who don't know what they're talking about is like maybe one of the worst ones. For them to talk about like they got to talk about like how it looks
Yeah,
the furthest back in history and blah blah blah. So I guess that was good. But
I guess, yeah. But yeah, this is
yeah.
a classic look at, well, not a classic look. It's a look at a cluster of galaxies doing some really cool things to galaxies even further back. Uh,
what?
Right.
I
So I
know.
want to just clarify for our listeners. So there's two pictures with that could be described as clusters of galaxies. And the one you're talking about is a deep field that has a cluster of galaxies in the foreground, but if you count the number of galaxies in that image, it's probably in the hundreds, if not thousands.
It's a few thousand. Yeah, there's a few
Whereas
thousand.
there's another image called Stephan's Quintet that is of an image of five galaxies that are very close to each other and much closer to us, still
Yeah.
tens of millions of light years away at least, but much more resolved. So we're talking about the deep field image here, Jim.
Yeah,
Deep
yeah,
field.
yeah. I mean, and of course, Hubble. One of Hubble's famous images is the Hubble Deep Field, and then they later did some ultra deep field. The deep field just means take your camera, look at one spot in the sky, and stare at that spot for quite a while, and that collects more and more and more light the longer you leave your camera exposure open. That's one way to kind of counteract having a smaller telescope, is leave the exposure open for a while. It doesn't help you with your resolution. You can get finer details, but you can collect more and more light. Um, this one is awesome for a whole huge number of reasons, but one of them is like this deep field was, I think, 12 and a half hours of exposure time, which sounds like a lot, and it is, right? I mean, there's a lot of people that want to use the web, and so if you're using up 13 hours of time, that's a lot. But the Hubble deep field was something like a week of
12
time.
days.
Yeah,
Yeah.
or 2 weeks of time. Yeah, I mean, it was much longer time to come up with a less deep field. So
Wow.
part of that is just the bigger,
Bigger
bigger
light
mirror,
collection.
more light. And in addition, some of the stuff you're looking at in these deep fields are galaxies that are crazy far away. And galaxies that are crazy far away tend to have their light redshifted by the expansion of the universe. So they tend to have their light, which is a lot of times in the visible, stretched out to the infrared, which is precisely, of course, what James Webb
Where
sees. And of course, this was one of the
where JWST
primary
looks.
reasons it was designed. It was designed to do this precise kind of thing, to see these ridiculously distant galaxies. And so some of those things, those little arcs of light you're seeing, are galaxies behind the main cluster. Most of the few thousand galaxies you're seeing in there are kind of all together-ish in space. But beyond that, way beyond that, are other galaxies which are having their light warped And so those kind of circular, semicircular image bits.
It's truly, yeah. I mean, it's science fiction-y stuff.
It is, and this is so
looking
good
at it,
that you can see the structure in those galaxies that are having their like to be able to see clusters of stars and structure within the galaxy in those galaxies that are billions of light years away is insane.
Yeah,
it is.
And you can tell a lot of we talked earlier a little bit about the colorization, but a lot of the sort of streaky bits and the parts that are being lensed, right? The parts that these older galaxies are actually behind this main fuzzy cluster in the center. Those are redder in the image, which talks again to how they did the colorization and the and where they are. But yeah, just like you even it's just if you like squint at it, you can see the sort of circles that are formed from the lensing, and it's I don't know, it's awesome.
Yeah, and then I mean the high res versions, I mean the full resolution versions, you can zoom in, and as Jim was saying, I'm looking at a galaxy whose apparent shape in this image is distorted by the warping of space-time from a cluster of galaxies closer to us. This galaxy is many billions of light years away, and I can see, like Jim said, I can see star-forming regions in that galaxy.
It's berserk.
Yeah. I saw one funny tweet that was like from somebody who's I think on the JWST team, who was talking about how like you guys are all ogling these images now and how great all these galaxies are, but when we were trying to calibrate the telescope, they were obnoxious. It's just like you're trying to point at a blank part of the sky and there's just like galaxies there mucking up your calibration.
Right.
But the other thing,
dark patches of sky.
Yeah, the other thing that's crazy about this, and we referenced the Hubble Deep Field, right? And we looked at this, is that like the fractal nature of the universe and how like some people saw this and were like, okay, it looks the same as that Hubble image, right? It's like you're looking and there's a bunch of galaxies and there's a bunch of stuff in the sky, but like. And that's because of sort of the more you zoom in, it's like that old Powers of 10 video, right? Where you're zooming out, you're zooming out. Like the more you zoom in, the more it looks the same because when you're looking at scales this large, there is just kind of like stuff everywhere and it's going to look similar, right? So even though we're zoomed even further out or even further back in time, it looks very similar to like the less zoomed image. So it's an interesting.
Yeah, that is kind of awesome. And actually, the differences are going to tell us a lot. Like they're going to tell us now we're going to be able to learn about the morphology of galaxies in the very, very early universe and how that compares to the later universe and all that kind of stuff. So there's it, and you get to do all kinds of things like see how much dark matter there is in that cluster of galaxies. And so I'm like, there's a ridiculous amount of awesome information piled into those deep field images. So
it's and. Those diffraction spikes we were talking about, so those show up for the stars. So when you see a diffraction spike, that's for our listeners, when you look at these images, like these distant galaxies, and you see these bright, spiky things, those are stars in our own galaxy right nearby.
Yeah.
And everything else you see, literally everything else you see is a galaxy with tens of millions to hundreds of billions of stars in each one. And they don't produce the diffraction spike because they're not a point source. They're this, even though they look, some of them very small, they're diffuse distributions of light. Really, really impressive. And it also, highlights, it's a big mirror, so it collects more light, but the focus that they've managed to achieve with this is basically at the theoretical limit of what you can do. And just amazing that it works. Well, now let's talk about something completely silly and not mind-blowing for a minute or two. I want to start with my follow-up Stumper. And Jim, you weren't on the episode for this Stumper, but...
Stupid question.
Great.
But it's not just a stupid question.
Okay.
It's Hollywood, philosophical, sociological, educational in topic area.
My favorite.
That's an amazing coincidence.
Yeah.
I'm belatedly catching up with this show on Amazon called The Boys about a bunch of superhero types, and it's sort of irreverent take on superheroes. And there was an offhand comment in the first episode about geosynchronous satellites at 380 miles up. And I was like, grumpy scientist knows that the geosynchronous satellite is 22,000 miles up or whatever. And so the stumper was, does anybody give a crap besides me? And what's my problem for giving a crap? So the follow-up to that is that there's lots of other wrong things in The Boys from a physics standpoint that didn't make me go, rawr, that's not possible. For example, one of the superhero guys is some A-Train who can run very, very fast. Well, it's physically impossible to accelerate as fast as he accelerates using the friction of your shoes on the ground. He's got an acceleration of many, 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 many Gs, and the best you can do is 1G acceleration with just running. And so, should I care? Which is worse? Or are they both? Am I just like, do I need to just get over myself?
I mean,
It doesn't matter.
It doesn't matter. Well, I think this goes back to some of the stuff of like, it's a different universe kind of, right? And like maybe different things apply. And as long as they're consistent in how they do that, we just sort of let it be.
The dude's got shoes that have a coefficient of friction greater than 1, Josh.
Okay. Well, there
they're
you
like
go.
Racetrack tires, right? Yeah.
Okay.
Yeah.
I mean, I have to say, I wasn't bothered. I'm not bothered by him running that fast, and it's partly because what Addie was saying is that nobody thinks anybody can run that fast. But people do know there are satellites up there, and there are satellites 380 miles up. Anyway, here's your real.
And that one, the satellite one, just seems lazy. Like you could look that up. You could very easily. Whereas it's hard to make the show about, if the guy's fast, you can't. How you get around
I agree. It. Yeah. Which is So I'm actually not bothered by A-Train running as fast as he does. Although I think I was bothered
by other things at some point.
I'm bothered by so many things that I shouldn't be bothered by. One of the things that bothered me about A-Train was that they were timing him, and it's like the reaction time of timing is like longer than the time it was taking him to do anything.
Yeah, just chip that.
Okay, here's your real trivia.
Okay.
We're talking about amazing astronomical photographs. The first person that we know of to look at an astronomical object through a telescope was Galileo. In the early 17th century. And the way he would record his observations was sketches. Look through with eye up to the telescope and make a sketch and make some notes in a notebook. On this day, I looked at Jupiter and I saw that there were 4 dots near it, and the next you draw sort of where they are and so forth. But at some point, we could start taking pictures of things in the sky. So your trivia is, when was the first photograph of an astronomical object made? And what was that astronomical object?
That's a good question.
All right, so you can think about that while we just briefly touch on the remaining 2 images from the initial release of James Webb
Can we just call it JWST or JWST or JW instead of saying the full name, please? Thanks.
Sorry.
It's okay. Also, I think one of the cool things about this is that like they obviously were very careful, and there was like behind the scenes negotiations about like which images they were going to release first. It's
a good set.
And it's a good set, right? But there was also a bunch of other data that's been taken. And it's continuing to collect data. So like there aren't going to be big giant releases for all of these, but there is just going to be a bunch more really awesome data coming out like rapidly. And so there's going to be super cool things to follow up on. And I think like the next AAS meeting, the big astronomy meeting, is going to be amazing, right? There'll be super cool results and planetary science results. So like some folks here at UCF are observing planetary objects in our solar system.
Yeah, that was the one bummer that I noted about this, is that everything here is distinctly outside of our solar system, which of course I love, but it would have been cool if there was one. But of course, it was designed for these deeper images.
And we do have a planetary result. I mean, that spectrum is a planetary result.
Yeah. So we mentioned already Stephan's quintet.
Stephan's quintet, SQ. Just call it SQ.
Oh, nice. I like it. Which is a in the sky quintet of galaxies, although they're not actually physically all grouped together. There's one of them, I think, that's not, and the other ones are.
Yeah,
that's right.
But this image is super unique because it's the biggest image they've taken so far. So it's a mosaic of a lot of different patches of the sky that they stitched together to make this really gorgeous image. So it's the biggest. So the deep field was the longest set of observations, and this one's the biggest on the sky.
And it, of course, it's got a gajillion galaxies behind also.
Yeah.
Yeah, you could certainly call this a deep field if you wanted to.
Yeah, right.
It's not the point, but yeah.
But this one's cool because
this is, of course, again, this is going to be the highest resolution we've ever seen this quintet in, and it's revealing all kinds of really awesome details about. Because what's the cool thing about this quintet is, like I said, 4 of those galaxies are really pretty close to each other in space, and they're interacting with each other. Their gravities are pulling on each other, and that's causing all kind of really interesting interactions in the stars and gas in the galaxies, and now we can see that. It's freaking awesome.
Yeah, like 2 of the galaxies are very close together. You can tell they have distinct cores, but they're definitely already merging and dancing, and then you can tell where there's this like material being pulled from another one that's pretty nearby. And the structure of the 5th galaxy, the one that's actually in the foreground, is very like distinct. Even though it's not interacting with those, it seems like it has just in this image, it seems like it has a very distinct structure.
It looks like it's been smacked.
Yeah, it's like more extended, and it has lots of like clumpy stuff that I don't know anything about this.
Yeah.
Well, that's not the.
Why is it shaped like that, Jim?
The one on the left is also part of that same group. What's the one on the bottom? That's the 5th one that is not really part of the group.
Oh.
So a lot of the, galaxies that are interacting with other galaxies tend to have more star birthing than other galaxies because everything's being mixed up and gas gets together and gets real dense and then starts making lots of.
You might even get an annular galaxy that way.
What's your favorite kind of galaxy? Spiral, elliptical, irregular, or dwarf?
I wanted to say irregular because it's like my digestive system.
I had the feeling you would go for irregular, but I wasn't looking for that particular imagery.
No, I apologize.
It happens.
I'm going to go with spiral annular. There's no such thing as an annular galaxy.
You just made that up?
I swear, it was lenticular.
You might.
Callback. It's a callback.
Callback.
Yeah, and so we know that the cores of these galaxies have supermassive black holes, and we're able to quantify that. And so it's interesting. I mentioned the circle of life earlier, and I was we talk about stellar evolution, but it's not evolution the way we use the term in biology, where evolution is changing, from one kind of organism to a different type of organism over many, many, many generations. When we talk about stellar evolution, we're really just talking about the lifetime, the life of a star. And galaxies have a life too. They start off with all kinds of star formation going on, and then in their older age, that tends to peter out. But then if they have collisions or interactions with other galaxies like we see here, that can affect their ability to form stars. And we were just recently in an episode talking about these bright young stars in intergalactic space that were produced by an interaction of galaxies. And so it's pretty cool to see that kind of thing going on. And all these different stages of the quote unquote evolution of stars and galaxies, really just their life cycles. And the last one,
image, last but not least,
the Southern Ring Nebula. Did I say nebula? Nebula.
Maybe. I do love a good planetary nebula.
Yeah, so here's my planetary thing. Okay, it's not a planet at all, but named planetary.
I studied planetary nebulae in undergrad, so and guess what? I studied dust in planetary nebulae in undergrad, so I'm just consistent in my words that I use in my research. Yeah, this one's beautiful. So planetary nebulae are always beautiful. So if you see images of sort of like, I don't know, they're often used in space image things because they're always colorized very nicely, and they're these big sort of blobs of beautiful gas and dust. And unlike what their name might make you think, especially if you listen to us a lot, planetary nebulae are actually like the end of a star's lifetime when it's exploded and it sends all this material outwards. And well, not exploded but when it's shed material dramatically and it sends all this material out and it's this gas and dust that's still moving away from the star, but it's still energized by that central star. And so you see it glowing and heating and all these different crazy structures.
Yeah, and don't have anything to do with planets. They're called planetary because in their early days of astronomy, they didn't twinkle like a star. They looked untwinkly like planets do, like a planet. Yeah. This is beautiful. And they released two different color composite images of this in two different parts of the infrared spectrum, sort of highlighting the different kinds of things you can see when looking at those. In one of them, you can see the white dwarf.
Because there's more than, there's one big mirror system, but there's multiple cameras aboard this thing. And so these are highlighting the powers of two of the different cameras that look in different wavelength regimes.
Yeah.
And one of the cool things, I always thought that really bright star in one of those images was the star that was losing all its stuff, but it's not.
Yeah, it's not.
A foreground star, right?
It's right next to it is the white dwarf, which you can see in the longer wavelength image.
Right.
You can see this red dot, which is the white dwarf, ironically, which is the sort of Earth-sized husk of the former star whose debris is now producing this big, beautiful nebula. To me, this looks like kind of a sub-oceanic pit or something with algae and stuff growing out of it.
Part of the reason it's gorgeous is it's not very symmetric, and I think part of that is that white dwarf is in orbit around that brighter star that you see. So having a binary star system causes this particular system to spew out its stuff in irregular ways. Oh, I shouldn't say irregular, but at least complicated ways.
Yeah, colloquially, you might say semi-elliptical. Okay, let's see what you think about our astrophotography history. When was the first photograph of an astronomical object made, and what was that object?
The moon.
Okay,
is my guess. And it was, I don't know. I'm bad at years right now. I can't. When did photographs happen?
Oh, that's part of the trivia. That's part of this. That's part of this whole. We know it was after Galileo.
Yep.
And before JWST.
32.
Okay, Jim, what do you think?
Actually, not a bad guess. I'll say it's Saturn just for fun, and I know they were taking pictures in the Civil War, which was 1860s. So that's why I think 1830s is a pretty good guess. I'll say 1826.
Oh.
Okay, you both did really well, but Addie was really almost smack on. It was the moon in 1840.
Oh, wow.
So
nice.
Very, very good for somebody who's struggling with years. Yeah. J.W. Draper. The next were in 1845, photos of the sun by Foucault of pendulum fame, amongst other things, and Fizeau, who I'm not familiar with, from Paris. These were long exposure daguerreotype images on these silver plates. It required a very long exposure, so you had to look at something very bright.
Yeah.
Objects. Sunspots were first photographed in 1858.
I thought maybe it would be when we were saying the things. I did think, oh, what if it was a sunspot?
Yeah,
but
not for a little bit later. And how astrophotography has come a long way in that time.
Yeah,
it surely has.
Yeah,
in
be sure to check out.
Period of time, geologically speaking or astronomically speaking.
Yes. Definitely check these images out. We'll post links to them on all of our places where we post stuff. While it may have felt like taking a home and transfer orbit to Pluto, it was just another episode of Walkabout the Galaxy. Give us 5 stars and we'll give you the universe. Be sure to follow us on Facebook and Instagram to get all our updates, and check out our website at walkaboutthegalaxy.com. Subscribe to our YouTube channel. Our videos now feature chapter markers so you can skip to the good stuff. Catch up on old episodes wherever you get your podcasts. Follow us on Twitter.
At walk_the_galaxy.
And ask us questions anywhere using hashtag AskWTG. Our theme music was composed by Richard Jurusik. Production assistance is provided by Logan Basinger. Thanks to our listeners in the north of England and around the world. Stay safe. I'm Josh Caldwell.
I'm Addie Dove.
And I'm Jim Cooney.
We're the AstroQuark, signing off until the next episode of Walkabout the Galaxy.